Okay, hello. Sorry I'm late. You should be able to hear me. You should see the desktop. Does everything seem okay? Does everything seem to be working?
Seems to be working.
Okay, great, thanks. Okay, let me think. All right. Okay, sorry I'm late. Maybe one thing I want to point out, my wife's been pretty sick lately. Professor Elias has been sick, and that's a lot of you have written me emails and have gotten answers, and that's the main reason why. I've been spending a lot of time having to help her. She's got an infection that's kind of stubborn and won't go away. So that's really taken up a lot of time. So I'm sorry if I haven't answered emails for a while, but I've been answering some, but others I just haven't had time to give the thought to them that they need. So so let's see. So if you send emails, please be patient. And then there's there'll be the take-home exam this Thursday. Let's see. Yeah, okay. So the exam will be, it's this Thursday, okay? And here's the review problems, okay? And I forgot to put a reminder. I should have put a reminder about it up here. I forgot to put a reminder, okay? So first, let me ask: does anybody have any general question about the review problems? Is there anything that any kind of question about the anything that seems like a problem with them, or anything general question anybody wants to ask?
So one problem that I was kind of getting stumped on, well, it was more like 13 and 14 with aliasing and the anti-aliasing.
Okay. Let's see. Now, okay, let's see. 13. Essentially, well, okay, let me download some. I mean, what the question is asking you to understand, figure out this picture here. Yeah, you've got some. Let's see now. Let me get the problem up. Okay, so you've got this line segment. Okay, and notice it actually goes from -1, 1, which was, if it was in the whole viewport, that would be this lower left-hand corner. It's -1, 1 up to 1, 1. So that's this upper right-hand corner. So it's going in the viewport, in the clipping, in the projection window diagonally. But the frame buffer is not square. See, if the frame buffer was square, what would the answer be? If the frame buffer was 10 by 10, what would the answer be?
The slope would be the same. The slope would be 1.
Yeah, so which pixels would get lit up?
Somebody just commented.
Yeah, exactly. The diagonal. Exactly. If the frame buffer was a square, see the clipping region is always a square, and this is the lower left-hand corner of the square, and this is the upper right-hand corner of the square. If the frame buffer was a square, you'd just be on the main diagonal: 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. But here the viewport is 10 wide by 3 tall, so now it's not going to end up being I don't know if I could, let's see. Okay, there's 3 wide. Let's see. and why isn't it? I was going to try and draw a picture of that frame buffer. Okay, so this is 3 by 4. If I highlight, did I do it 3 by 10? 1, 2, 3, 4, 5, 6. Oh. 3 by 10 now, right? 3 by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so it's 3 by 10. Okay. And that's not the line segment anymore. Okay, but now the line starts down here because that's the lower left-hand corner, and the line ends up here because that's the upper right-hand corner. And the question is, as you go, like, which of these pixels are going to get lit? Yeah. So there's just 3 rows of pixels, and you're going to go from the lower left-hand corner to the upper right-hand corner, and it's representing a 45-degree line, but it's not a square. Since it's not a square viewport anymore, 45-degree line isn't a 45-degree line. Okay, so now you have to use the formulas from the you have to use the formulas that come with it came with your last homework assignment. So the formulas you need the formula sheets in the homework assignment. It's also in that folder that's called renders. Okay. All right, so you need this. Where to go? It's opening on the other monitor. Okay. Okay. Okay, so you have to use these formulas to figure out exactly where you are. Well, actually, we know exactly where we are. Okay, we actually don't even really need them because the picture we drew just shows us where we are. We're starting at this corner, and we're ending at this corner. Okay, and then you could actually just draw. You could even with a paper and pencil, you could draw the line from there to there. You could draw the line from that point to that point. Okay, and oh, I don't, I don't have a program. Yeah, I don't have a draw. Yeah, with a drawing tool. Let's see. You see what I mean? You could draw the line from there to there. If let me clean this up a little bit. What would you do next if you drew that line? I think I'm trying to think of a drawing tool to let me draw that line. What would you do next after I drew the line from that point there to that point there? What would be the next step without even using the formulas, but doing things visually? What would be the next step?
Would it be figuring out which pixels to turn on and off?
And how would you do that?
So whichever is closest moving up, if it's closer to the center of the pixel or the, I can't remember what it's called.
Okay, the dots are called, what do we call the dot?
I can't remember. I know there's two different names. There you go.
The logical pixel, yeah. And the square is the physical pixel, because the square is what actually gets drawn on the monitor. The monitor, the monitor actually lights up little squares of light. The monitor physically lights up little squares of light. Okay, so, and then, but the dots represent what we logically think of as the thing that represents that square. Okay, now, let's see. Does anybody have a suggestion? What would let me draw the line here? I mean, okay, I know. Play a little trick with tools. Let me take a screenshot. Let's see. Take a screenshot. Open it in Lerp Formula view. I don't know why Windows is not cooperating with me. Here, open it in Lerp Formula view. I don't have search on my Windows won't let me search here. Okay, so here's Lerp Formula view. There's my screenshot. Go ahead and crop it. Okay. Now I think Lerp Formula view's got a drawing tool built into it. My memory is that there's a drawing tool. Yeah. Cool. Okay. There's the line. Okay. All right. So now, okay, this pixel's turned on full. Okay. Now, in this column, which pixel would I turn on?
The bottom one.
The bottom one. This column.
The bottom one.
Bottom
again.
one. This column.
The middle one.
Yeah, now you move up. Middle again. Middle again. Middle again. Oh, here's an interesting one. I don't even, it looks like it's almost exactly in the middle. I think the renderer rounds up. I think, but I don't even remember for sure. Yeah, it looks like it's literally here by chance, just being right in the middle. So I think the renderer rounds up. This top row. Okay, but now now that algorithm, like this one, 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 this one. Which algorithm is that? Which rasterizing algorithm is that? See, the problem we started with was about anti-aliasing. Okay, actually, well, see, first it says anti-aliasing false. Then, oh no, let's see. Problem 13 is, 13 is with anti-aliasing turned off, right? And then 14 says redo it with anti-aliasing turned on. Okay, so what did we just give the answer to? Yeah, so
13.
13, yeah. Now let's, okay, so we just gave the answer to 13. Okay, so which, so that pixel, 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 this one, this one, this one. That's the algorithm with anti-aliasing turned off. Now 14 says do it with anti-aliasing turned on. Okay. What do I change? What's it? Yeah, that's the line. Here is the line with no anti-aliasing. So you turn on, for example, the line is closer to that pixel. You turn on the whole physical pixel. The line is closer to that logical pixel. You turn on that whole physical pixel. You turn on that whole physical pixel. You turn on that whole physical pixel. Aliasing does, the anti-aliasing then does what?
Is it every pixel that it touches?
No, unfortunately, touches is, you can't think in terms of touching. It's not every pixel that it touches. Because I could make it not touch a pixel and still light that pixel up. It almost happened right here. See, the line barely touched that pixel, and if I drew it a little bit different, it would not touch that pixel, but you would still light it up. Okay, because I could have had the pixel, I could have had that line come just right through that. It could have come, yeah, it could have actually come just to the right of that X, that crossing point. What's the rule for anti-aliasing? It's not does the line touch the pixel. The key is to look at that line segment between two logical pixels. Look at that line segment between two logical pixels. What's the rule? What would think in terms of just common sense. That line, the line we're drawing, is somewhere between that pixel and that pixel. It's a little bit closer to that pixel than it is to that pixel. But what's a nice common sense rule for how to light up those pixels?
Use them both half intensity.
Okay, that's that's a common sense rule, since somehow it's between the two of them. So why not give this half this intensity and this half the intensity? But there's actually a way better rule than that. That's on the right track, but there's something much more sensible to do than half and half. What would be a better strategy than say, okay, it's kind of straddling between two pixels. Let's make them both equal and make them each half. What would be a better strategy? Okay.
Oh, use the Lerp formula to.
Well, okay, yeah, and but that's saying math. Say what it really means.
Oh, okay.
Based
on the. Oh, maybe I can't say it.
Oh, it's common. It's real easy, simple. It's easy common sense. Lerp is just a fancy way to make something that's very common sensible. This line, which is right there, is between those two logical pixels. How do we light them up?
Wherever the diagonal is closest to the logical pixel in that line right there, give more intensity to
the one it's closer to. Yeah, yeah, if you're right smack in the middle, it's 50-50. As you move closer to one pixel, it should get brighter while the other one's getting dimmer. That would make the most sense. Yeah, if you're right smack in the middle, yeah, then okay, 50% of weight here and 50, half intensity here and half intensity here. Okay, but if you're like, look at this one. How should the intensity be split between those two logical pixels?
Like 90-10 or something like
Yeah,
that.
like almost all the weight's going to be on this pixel, and this pixel's going to be almost, this will be almost white, and this will be almost black. Or in this case, this would be almost black, and this would be almost white. Okay, now that's what Lerp does for you. Lerp says, if you're 3/4 of the way between those two logical pixels, if you're 3/4 of the way between them, this one gets 3/4 of the light, and this gets 1/4 of the light. If you're 1/4 of the way between those two logical pixels, this one gets 3/4 of the light, and this one gets 1/4 of the light. You see, if you're 1/4 of the way from here to here, you're closer to this one, so this one should get the weight. And then that's this Lerp formula here. See, then there's the Lerp formula. Yeah, depending on t starts at 0 here, t ends up at 1 here. As t moves across from 0 to 1, you ask, where do you hit the line? And that's the value of t you use for weight. So you use 1 minus t on the left one, because when t is near 0, you've got more weight on the left one. When t is near 1, you've got more weight on the right one. And this splits the weight between the two, because it's 1 minus t, t. So the full intensity is split between that guy and that guy. All right. Now, go back to our picture over here. So we're switching now from the non-anti-aliased, or we might just, that's a double negative. Non-anti-aliased is sometimes called the aliased version, because the two negatives cancel each other. So the not anti-aliased one was light this one fully, light this one fully, light this one fully, light this one fully, this one, this one, this one fully, light this one fully, this one, this one. Okay, now what do we do with the aliased one? What do we do in this column? What do we do in the first column? What's t in this Lerp formula?
See, some people are commenting to light up the bottom pixel full.
Oh, yeah, because what's t? What's t in the Lerp formula? In the first column, what's t in the Lerp formula? T is 0. Yeah, t is 0. So all the weight goes here. Okay. Now you move to this column, and if you actually want real numbers, then you have to use the formulas you have to then start using the formulas if you want to use real numbers. In fact, suppose we wanted to use real numbers to kind of finish this problem. We could actually do that. Okay. This is logical pixel 0, 0. And this is logical pixel 3, 1, 2, 3, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is logical pixel 9, 2. I'm sorry, because you count. So this is logical pixel 9, 2. This is logical pixel 0, 0. Okay, so the logical pixel down here, see, can I don't know if this is where Earthframe View probably won't let me, oh, I know. Wow, I've lost my ability to type in to this stupid box up here. I wonder what I did wrong. I can't type into, I have to search for things. Anybody have any idea why I would lose the ability to type into this thing? I don't even know where paint is. can that break?
You can just type paint.
It won't work.
Oh, it won't. Oh, sorry.
Yeah, it's bizarre. I've never seen this happen. My ability to just open, you're supposed to be able to just click on start and type word, and it'll search automatically. And Windows is a mess of an operating system. I mean, this kind of stuff happens all the time. Features, I mean, if I reboot, it'll probably fix it. I don't have time to reboot now. But I've lost the ability to type into. There's probably some stupid little thing.
You can press Windows and the Windows key.
Oh, try from the keyboard. So that's a good it's a good idea. Open it from the keyboard. Still not working.
Can you do like Windows S?
Oh, Windows search. Still nothing. Wow, nothing. Well, okay.
Or all apps or something.
No.
Okay. Oh yeah, it's not there though. Those are all the apps. Sorry.
Yeah. Does anybody know what they would call Paint program? Since it's not called Paint.
No, that's not it.
Huh?
I was thinking that Paint 3D, but that's not it.
No, that's it. I'm not. I played with it. I don't know it very well. You think they would call Paint, but I think they actually have another name for Paint. I think it's. Oh, under accessories, there. Paint. There it is. It's under accessories. Right.
Good to know.
Okay. Now, down here, that was pixel. That's pixel 0, 0. Okay. And up here, this is pixel. What did I say it was?
10.3.
No, 9.3. 9.2. Yeah, because it's 10. But we count from so it's 9.2. Okay. All right. So now write the equation of the line that goes from 0, 0 to 9.2. Okay. So I want to write the equation y equals m times x plus b. Okay. Well, I know what b is. B is what?
0.
0. And I can figure out what m is now. What's m?
2/9.
2/9. Yeah. So 2/9. Okay. So there's the equation of that line. Okay. Now that point right there would be that would be y of 1 equals 2/9. Okay. That was easy. So y of 1 is 2/9. Okay. So that means that, okay, what's 2/9 in decimal? .22222. Okay. So that's 0.22222. Okay. So how are these pixels lit up? Now I've actually done the calculation. I found that line. I got the equation of that line. I can plug in logical pixel 1. I'm in logical pixel 1 column. I got y of 1 is 2/9, which is 22222. So what do I do with these two pixels now?
Light up the bottom one 80% and the top one 20.
Rounding. Okay, the bottom one is 80%. The intensity would be 0.888, or if you want, you could do 1 minus 0.222. Okay, so this one would be 1 minus 0.222, and this one would be 222. Okay, all right. Now what about the next column over? Okay, so 0, 1, 2. Okay. Do another logical pixel, y of 2 equals 4/9. Okay, so 4/9 is 0.4444. Okay, so you'd go now here. This would get this one would get 55% of the weight, and this one would get 45%. Okay, see 1 minus 4/9, that's the weight down. This would be 55%. The brightness of this one would be 55. The bright one of this one would be 45. Okay, then you could do one more. So y of 3 is going to be 6/9. 6/9 is what? 2/3. Okay, so that one's pretty easy. This one is going to be one. Now notice we're moving away. We're moving closer up to here now. It's going to be 1/3 of the weight here and 2/3 of the weight here. Okay, let's do one that's more interesting. 0, 1, 2, 3, 4, 5. Let's do 5. Okay, let's do y of 5. Y of 5 equals, okay, that'd be 10/9. Okay, go over here. 10/9. Oh, great. 10/9 is, okay, 10/9 means something. See if I can get Google. Yeah, okay. So, all right. So now, okay, what am I? Okay, so I'm in column 0, 1, 2, 3, 4, 5. I'm in this column here. The 2 pixels are this guy and this guy. Okay, how's this guy lit up?
8/9.
89%, right? 89%, and this guy gets
11.
11%. Yeah, 89% and 11%. Okay, 89% here and 11% here. Okay, let's. Okay, what about this one? It looked like it was right. Oh, notice it's really almost right in the middle. Now that one's 0, 1, 2, 3, 4, 5, 6, 7. So one more. Let's do y of 7. Y of 7 equals 14/9. Okay, over here in the calculator, 14/9. See, 1.555. See, it was actually, yeah, and it didn't need to round up. It actually was a tiny bit closer to the top one. It was 1.55555. Okay, so it's real close. So this one's 55% and this one's 45%. So this one's actually 55/45. Okay, all right. So we can go through. Yeah, and the key is, if we got the picture of the window. Okay, so back in this problem, if we visualize it, we actually build that frame buffer. Okay, so there it is. There's that frame buffer, 10 rows by 3 rows of pixels. Okay, we know that this one is the lower left-hand corner. That's how I made the problem supposedly easier. I made it so that you just knew that this one is the lower left-hand corner and this one's the upper right-hand corner. Because in the original window in camera space, this is the lower left-hand corner of the view rectangle, and this is the upper right-hand corner of the view rectangle. So you know you're going from that logical pixel to that logical pixel. Write the equation of the line, write the equation of the line, and then I can start calculating the weights at 1, 2, 3, 5. Yeah, I can start calculating, and I can actually say exactly how I would weight each pixel. Okay, all right. So that's how you could step through that one. And actually, I was a little bit wrong. We didn't need the formulas from the formula sheet because you didn't need to compute that left-hand endpoint and that right-hand endpoint. The formula sheet, this is where we would have computed the left-hand endpoint and the right-hand endpoint if we didn't kind of know where they were automatically. If we didn't know automatically where in the view plane, which logical pixel we were at. Yeah, if we didn't know which logical pixel we were at, where the line segment started and where it ended, we would have to do this calculation here. But I made this problem so that you just knew you were starting in the lower left-hand corner and starting in the upper right-hand corner. So that, I mean, you could still do the calculation. Yeah.
So if you were to give a problem like this on the midterm, would you like us to draw like a diagram like that and just like write at what percentage the pixels will be lit up at?
Yeah, that would be a good answer. And you could you could draw that picture and you could write out your formula. Label. Pretty much exactly what I did here. Notice I drew a little picture. I'm not going to give you 273 pixels by 88 pixels. It's going to be like this. If there's a problem like this, it's a small frame buffer. Okay, so you could very quickly draw the frame buffer. You could draw that line between. You may have to calculate where that starting point is and where that ending point is. If in that problem, where's the problem? If I'd have made this a kind of funny, like if I'd have made this 0.7, 0.4, if I'd have made this 0.7, 0.4, well, who knows where in here that would land? I'd have to do the calculation. I'd have to figure out where that point land, where does it land in the pixel plane? Same with this one. If that was some point like negative 0.7, negative 0.8, I would have to use this formula to find out where I was landing. Where from the projection plane to the pixel plane, where I went. See, these coordinates are in the, now notice these coordinates are already in the projection plane. See, that's another thing. Another thing I did to make this easier is these coordinates are already in the projection plane. Now, if I made the z variable different, what would you do then? Suppose the z variable is -7. What if that was a -7?
Well, you've got to project it to the view
Yeah, so you'd
plane.
have to go back to step 1 and do the projection first. So I could make the problem harder. I wouldn't want to, that would be mixing up a lot of steps. But if this was not already in the projection plane, you'd have to go back here and start with the projection formula. That would give you the points in the projection plane. Okay. Then from the point in the projection plane, you find the point in the pixel plane. Okay. The point in the pixel plane is which one of these, where is it in this plane here? You usually won't land on a dot. Usually it'll be close to a dot and then you round it to the dot. You take the starting point, the algorithm rounds the starting point to a logical pixel and it rounds the ending point to a logical pixel. Here I gave you a starting point and ending point that don't need to be rounded. Okay, but I did that on purpose. So I could test the whole, you could do the whole algorithm. I could test that you could do the whole algorithm by asking you to do this problem where this point is not in the projection plane, this point's not in the projection plane, and they don't project to logical pixels, and so you'd have to project them to the view plane, then you'd have to move them from the view plane to the pixel plane, and then you'd do this algorithm we just did. The final step was once you've got the starting logical pixel and the ending logical pixel, you can write the equation of the line between them and start moving across and computing the weights. Okay, but I don't like to make a problem test everything, because there's if you make one mistake early on, then it becomes impossible to grade it. Actually, if you make a simple mistake in the first step of a problem that tries to trace through the whole renderer, if you're trying to use these formulas through the whole render, if you make any little mistake, like even in the first step, then everything afterwards ends up being slightly off. It becomes hard to grade. So I tend to ask questions that only ask one step of the render at a time. But yeah, for the asking what pixels are lit up, probably the best way to do it is the picture. Yeah, so you have a visual aid to help you. So you see the pixels, you see the line, you can do the calculations, and you kind of know ahead of time what they're about, what they're going to almost give you. Like here, you could say, well, it's almost going to be like 70% here and 30% here. Here it's going to be almost like 60% here, 40% here. This is going to be almost 80% up here and 10%, 10 or 20% down here. So you know from the picture what your ballpark answers are, and then you do the calculations to get the exact one. So this little picture right here would be the best strategy. Okay, if it's the aliased version, then you don't this picture still helps, but you don't have that extra calculation. If it's the aliased version, it's just which pixel you're closest to. This one, 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 that one. Okay, so if it's the problem with aliasing, like in this case, problem 13 with aliasing, you can give me the coordinates of which pixel are lit up. You can say, oh, you light up pixel 00, 01, 02, 13, 23, 33, 43, 52, no. This would be 72, 82, 92. Yeah, 72, 82, 92. So you can tell me the coordinates of which pixel are being lit up. Because in the alias version, you either light up a pixel fully bright or you leave it fully dark. Okay, so for the answer to this one, you could list the coordinates of the logical pixels that are being lit up. For this one, you would want to give the weight on each logical pixel. So you could write out your answer as this pixel with pixel 00, 100%. Pixel 01, I forget what it was. Like 01 was say 90%. 02 is 10%. 03 is say 70%. No, sorry. That'd be 101 is 70%. 1 no, I'm sorry. 02 is 70%. 12 would be say 30%. See, so you could go through and give the coordinate and the weight for the pixel. Coordinate and weight, coordinate and weight, coordinate and weight, coordinate and weight. Okay, so you could give your answer in a way that way. Okay, so then you're then you're really seeing what the render is doing. Oh, and then how can you double check if you're at home? What do you do to double check this answer?
Use your renderer and write a small.
Yeah, I mean, the code, it's almost right here. I don't know if you need much more than that line, that line, that line, and those lines. You can just, almost make a program out of this. Did I get rid of the text? Create a frame buffer, create a model, add a vertex, add another vertex, add the line segment, create the scene, add the model to the scene, turn off anti-aliasing. Let's see. I think that's it right there. Just wrap that in a program. You do the you need the imports. Wrap it, wrap it in appropriate. Yeah. So I think that's it. I think that's pretty much the code. And then then you should see the when the renderer will dump everything out because of the these three debugs. See, the pipelines, the debugging is turned on in the pipeline. Clipping debugging specifically is turned on. Anti-aliasing debugging is specifically turned on. But do anti-aliasing is turned off. So the anti-aliasing debugging is turned on, but the anti-aliasing itself is turned off. Then render, and then also print the frame buffer. Another thing you do is you can actually print the frame buffer itself. The frame buffer has a two-string method in it. The frame buffer's got its own little two-string method. The frame buffer will give you it'll dump itself out, and then you can see what's stored in the contents of the frame buffer. So it's a little bit harder to read, but it'll give you the same answer. So you'll get the answer two ways. You'll get the answer from the render's debugger, and you'll also get the answer from the frame buffer being dumped out. So you should see the answer. If you do this, if you use this code, you should see your answer printed out actually two different ways. Okay, so that's a good problem. That's a good problem to have done here, because that stepped us through a fair amount of the ideas. Okay, all right. So that was 13 and 14. So you kind of do them together. What about this one? Any other question about this one? How we did it? Anyway, any other question about how we did this one?
So I know you mentioned using the formulas. Like I wrote up the formulas, and it makes sense the way you just eyed it, transferring from, the slope. But I still got a different answer when you switch the vertices using the view plane to pixel plane transformation formula.
Oh, you mean you didn't start here and here?
Yeah, I got like different points that.
The starting and ending, or these ones in between?
The ending point. So for the first vertex, you get 0, 0. I got half and half. X is half and Y is half. And for the second vertex, I got 10.5.
Oh, because they'll round to this.
Okay.
Yeah, they should round to this one. Yes. Yeah, you're right.
Are you talking about the fourth formula?
Yeah, let's see. Now let's see. Where's the problem? Okay, here's the problem. You're right. See, that point is the extreme lower left corner. Okay, let me build the Java doc and look at the picture of the yeah, I can answer that by opening the Java doc and looking at that document that describes the render. Okay, so
I think I figured it out.
yeah, you're right. I actually glossed over that. You end up in the extreme lower left-hand corner of the pixel plane, but then that rounds you to a logical pixel. So I was right about what pixel to land on, but I skipped a step. So I got to that pixel without actually using the calculation. So I glossed over one step. And you're right, I glossed over one step. Here it is. Okay, here's rasterization. See, right. See, there's that point, right? Our vertex was sitting in the problem. Our vertex is at -1, 1, extreme lower left-hand corner, right? The other vertex was 1, 1, extreme upper right-hand corner, right? Then you're right. You transform them to the logical pixel plane. This lower left-hand corner is going to transform to that point there, right? But that's not a logical pixel. So then where do you round to? Him. See, there's in the formulas. Where's my formulas? Too many windows open. Where did
I think I
have
just saw it.
Yeah, it was a PDF document. It's the PDF viewer. It's down over here. Okay. It's this rounding here. It's actually down here that we round to the pixel. We have to go from the pixel plane to the pixel. It's this rounding step that's going to round me from that corner there, which is 0.5, 0.5, to that guy there. Okay. Oh, and that's actually 1, 1. Oh yeah, I forgot. I mislabeled. Yeah, this should have been 1, 1, and this should. Yeah, I forgot that I was. See, there's no hardcore rules about how you should do this, and sometimes I forget exactly which choices I made. Over here, yeah, I made this 1, 1. This is the lower left-hand corner is 1, 1. Because see, this is 0.5, 0.5, so it rounds up to 1, 1. So I actually this should have all been redone with 1, 1 there and 10, 3 there. Yeah, the way I've got it set up over here, this is 1, 1, 10, 3. Yeah. So this is, and see here how the upper right hand corner is window plus 0.5, height plus 0.5. You never quite land on that vertex so that everything will round down to that guy. That guy is WH. Okay, it's W rows up and H rows over from 1, 1. Okay, so I actually should have labeled this 1, 1 here and 10, 3 here. Okay, that'll change these formulas a little bit, but it won't change the weights. It'll just make those formula, just change the numbers here, but it'll end up giving us the same weights. Okay, but so you're right, you did the transformation right. You ended up at that point, but then you round to that logical pixel. And we always start the line at a logical pixel. So always start the line at a logical pixel. So I don't draw the line from this corner here to that corner there. Okay. Yeah, the algorithm is not to draw the line from that corner to that corner. It's to draw it from that logical pixel. So that corner rounds to that logical pixel, and that thing rounds to that logical pixel. Then draw the line between them. Now, if you do draw the line from this lower left-hand corner to the upper right-hand corner, you'll probably get the same answer. Yeah, it doesn't change things by very much. So you would, for the most part, get the same answer. And some renders may actually do it that way. Some renders, when they convert from here to here, they may not round to a logical pixel. Yeah, you don't have to round. All the renders, all the code I've looked in all the textbooks to make things easier, they round. So when a vertex transforms to here, you round it, the starting point. When the left-hand endpoint rounds to somewhere in here, when it transforms to somewhere in here, round it to that logical pixel. When the other endpoint transforms to somewhere in that box, you round it to that logical pixel. Then draw the line segment from logical pixel to logical pixel. Tends to make the code easier. It makes the code a bit easier. Okay, so that guy, like you calculated, he'll round to there because 0.5 will round up to 1 and 0.5 will round up to 1, so you'll be at 1, 1. And you won't ever land on this corner. The reason you won't land on that corner is because of this edge is really not part of, this edge here is really not part of the view window. There's an inequality. Yeah, the transformations are set up so that this edge is not really included, and neither is this right-hand edge. There's an inequality involved. So you can end up on this left edge or this bottom edge, but not the top edge or the right edge. Because if you landed on the right edge, you'd round to the right. You'd round off of the frame buffer. That's a problem. So you have to exclude that right edge. Otherwise, you would round off of the frame buffer. Same thing. If you allowed that top edge, you would round off of the frame buffer. So we have to have careful inequalities to exclude the top edge and the right edge. Okay. Here, see there. We're excluding the top edge. See, we include the bottom edge. We don't include the top edge. Actually, I should have had this is strictly less than 1 here and strictly less, but yeah. Because we don't include the top. Yeah, I should have said the same thing here. Don't include the top edge, don't include the right edge, don't include the top edge, don't include the right edge, because they cause problems. They'll round you off of the viewport. See, so don't include these. So you would always round to this one here. Okay, so you're right. You start at that point there in the lower left-hand corner, but then it rounds to there. But if you did the problem with that point, if you'd have drawn the line from there to there, you would have pretty much got the same answer. So it wouldn't cause you to be off by a lot. In fact, it would probably give you the exact same answer. You know, you'd be off by such a tiny amount that it wouldn't change the weights on these pixels even. Okay, so that's a good point. So I tried to make the problem easier by making it sort of obvious which was the starting pixel and which was the ending pixel. But if you use the calculations, then you had to remember to do the rounding step. Yeah, because you'll land there and then you have to round to there. And you'll land there and you have to round to there, to that logical pixel. Where is it? There. Okay, so that's a good. So, but yeah, notice the problems are really to get you to think about. Yeah, so you're thinking about the formulas, so that's good. Yeah, thinking about the formulas is the right way to do it. You know, you're getting the right answer. You're using the formulas right. Okay. Okay. What about other question from this? Anybody? Another question about this one? Because what we've done is pretty much, we've gone from here to here to here, which is a lot. You know, that's a big part of understanding the render, going from the view plane to the pixel plane to the pixels. Okay. And so that's what we've been talking about. This picture here is actually a combination of the pixel plane and the pixels. See, when you draw the little boxes around the logical pixels, you're essentially superimposing these two pictures on each other. In the center of each one of the pixels is a logical pixel. In the center of every pixel is a logical pixel. Okay, so sometimes we think of them as separate entities. Sometimes we just put one on top of the other and treat them together as the pixel plane and the pixels together. Logical pixels, physical pixels. Other questions about this one? What about other problems from, what about other ones from the review? That was a real good one. That's one of the problems.
I was going to say, I had one quick question about the row major form, just so I'm not one off. The indexing starts at 0, correct?
Yes.
So it'll go from 0 to 599 for the first row, and then 600 to whatever.
Yeah, which problem was that? Remind me. I don't remember.
Number 11, I do believe.
Okay. Now they're Java arrays, so certainly, yeah, indexes always start at 0.
All right.
So if it's a two-dimensional array, you have 2 zeros. You have the 0th row and the 0th column. And if it's a row major one-dimensional array, then you have 1 0, but it's the starting point. And that's the beginning of the first row. So, but yeah, Java arrays are always indexed from zero. All arrays in Java are indexed starting at 0. Okay. So this one gives you a one-dimensional array that's 2400 pixels. Or it gives you a one-dimensional array of size 600 by 400. So 600 times 400. So 240.
It'd be 0 to 23,999.
Yeah, exactly. Yeah, it's a new. Yeah. So the first index would be 0, and the last index in that row major array would be 2,300 and two. What is that?
239,999.
Yeah, 239,999. That's the last index. Yes. So yeah, definitely, and you have to definitely you have to keep that in mind. Yeah, you got to definitely keep that trick in mind. That it's now I lost where I was.
PDF. Yeah. Oh no.
Yeah, oh yeah, the exam was on the PDF. Where did the PDF go? Oh, there it is. Okay. No, those are the no, the PDF was the equations. The exams in the, oh, it's in the browser tab. Oh, I'm sorry, there it is. The exams in the browser tab. Okay, so, yeah. And, yeah, so, yeah, figure out where that is. How, yeah, each row is 400 pixels wide. Yeah. So you need, yeah, so, yeah, you,
I think you said that backwards though. I think it's 600 wide.
oh, yeah, you're right. Yeah, it's 600 pixels wide by 400 pixels tall. So each row is 600 pixels wide. So, yeah. So this is row 257, right?
Right.
So that means you have to skip over 256 rows of that big. So you have to have 256 times 600. You have to skip over all those rows. So now you're at the beginning of row 257. Then you go that far into that row. So the answer would be 256 times 600 plus 188. See, you skip over, you're in row 257. Oh, no, you got to be careful. No, you're not. No, you're not in row 257. You're in row what? You're in row number 257. So that's the 258th row, right? So that's the 258th row. So you have to skip over 257 rows. So you have to take 257 times 600 to skip over 257 rows to put yourself in the 258th row. And then you're that far, well, then you're 189 positions into that row. Your number 188, since you're starting to count from 0, is the 189th position in that row. But you just add 188 because you're starting out counting at 0. So you just have to think a little bit about what this means. That's the 258th row. So you have to skip over 257 rows. And that's the 189th pixel in that row. So you have to skip over 188 pixels. Aren't you glad they started counting at 0?
I think maybe you were right at the beginning and I confused us. Is the y coordinates the rows actually, and the x coordinates the columns?
Oh, let's see. This is row. This is column.
Okay, but the y goes downwards, right?
Yes. Mm-hmm.
So then,
so 600 pixels wide, that's the y coordinate, goes from 0 to 599. And 400 pixels tall means the x coordinate goes from 0 to 399. So this coordinate goes from 0 to 399. And this coordinate goes from 0 to 599. Row, column. So these are the range of, yeah, they're 600 pixels wide, so that's the range for the column numbers.
right.
That's the range for the row numbers. And the row numbers are the first one. No.
Aha.
Yeah.
So there's actually
Oh,
y.
no.
There's
Okay.
y rows, right?
Yeah. Why is this confusing as hell? There's two things. I mean, everybody, first of all, you're counting from 0 instead of 1. And then the other issue is arrays and 2D coordinate systems in calculus can be treated differently. You've got to worry about how, in calculus, x coordinate measures left and right, and y coordinate measures up and down. Okay, now with arrays, not everyone agrees on how arrays should be. The first coordinate can measure the row. A lot of times the first coordinate is row.
Right.
So that's measuring up and down. So that's like the y coordinate in a math class. And the second coordinate measures column.
Right.
That's up and down. Mm-hmm.
Yeah, but our frame buffer goes.
Yeah, and I had to make decisions about the frame buffer. Should I make it more Java-like or make it more calculus-like? Okay, and I thought I made it the way Java makes their frame buffers. My memory was I aligned my choices with the way Java does their choices for their frame buffers. And yeah, go look it up. It's confused. Yeah, I'll mix it up. I know I mix it up all the time because there's an inherent confusion because people tend to think of tables as rows and columns. They think row number first, then column number. But row number is a vertical displacement. That's a y coordinate in geometry class, and column displacements are horizontal displacements. Which column you're in is measuring horizontally. That's an x coordinate. So there's an inherent confusion with these things. And this problem comes up all the time when you try and translate math into Java and C and C++. And pixel and viewports and frame buffers.
Right.
Look
So,
up.
Just so I have this straight, our frame buffer in the upper left-hand corner is 0, 0, and it goes x coordinates wide and y coordinates down. Correct?
I
So the 188 is the row we're going to, right?
you know the old saying, read the source.
Right.
Let me look up get pixel. Oh, here it is. No.
Yeah. Y is height.
Yeah, see, there's the little formula. There's the right formula. There's the right formula.
Yeah, so Y is the rows actually.
Mm-hmm. Yeah.
Okay.
Yeah. There's no law, Congress didn't pass a law about how to do this. And believe me, Microsoft has one way of thinking about it. Google's got another way of thinking about it. Adobe has another way of thinking about it. Java has another way of thinking about it because no one agrees on exactly how all this stuff should line up. Fortran doesn't count indexes at 0. Fortran starts them at 1. Java, C++, and everybody else starts indexes at 0. Julia decided to go at Fortran. They started their indexes at 1. The Julia language
starts at 1 as well.
Pardon me?
MATLAB starts at 1 as well.
MATLAB starts at 1 too. See? Yeah, you just can't get everyone to agree on this kind of stuff. You can't get anyone to agree on this stuff.
Right.
Yeah. So you go look at the code. What is the code actually doing? And I forget what my own, that's why you document your code, because you will not remember what your code does 3 days after you wrote it.
Right.
Okay. So I try to document it. Okay.
Right.
So the answer is that's how it's done. There's how it's done in the code. That's how you should do it. Okay?
Yep.
That's a good question because, turn to the code. Look, a lot of times answer the questions by looking, how did the code do it? And one thing that's tricky here was that the frame buffer and the PPM files don't agree. If I remember right, things have to be switched for PPM files. So, what's row 0? Is row 0 at the top or is row 0 at the bottom? That's another problem where people disagree. Should row 0 in a picture be the top row or the bottom row? No one agrees. Because an array doesn't really have a top and a bottom. It's got a first and a last. But when you draw it on the screen, you got to say, okay, first row. Does it go at the top of the screen or the bottom of the screen? Guess what? 50% say one way and 50% of people say the other way. Not everyone agrees where the first row should be the top of the screen or the bottom of the screen.
Yeah, is the cup half full or is it half empty?
Yeah. So you any given system you're working with, you got to go look at their documentation and sort it out. And I don't even remember in this case all the decisions I made. Like, you know, like, oh, it's row 0 at the top or bottom. I don't remember. Actually, right now, I don't remember which one I did. I don't remember if row 0 is the top or the bottom of the frame buffer. I think it says here somewhere. But okay, we run out of time. Those are good. Those are good questions. That's the whole point of the goal of his review stuff was to generate good questions so you can keep talking about these ideas. Okay, so probably do the same thing on Thursday. If there's more questions, we can look at more problems on Thursday too. Okay, so if anybody's got any questions, send them to me by email, and I'll try to answer them. And okay, so is there anybody got a last minute question? Anybody have a last minute question?
Professor Kraft, I know I was supposed to meet with you after class today. So I know I didn't realize your wife was sick. So I don't know if it would just be better to email you.
Well, if you want to meet, we can still meet. You know, give it a few. Yeah, but I may. Yeah, let's meet for a few minutes and then see what the questions are.
Okay.
Okay. All right. Okay. So I'm gonna go ahead and stop the sharing and end the meeting. And if you haven't voted, go vote. And see you on Thursday. Okay. Bye-bye.
Bye.